Hello and welcome to this vignette on bias considerations when building a statistical model. This vignette gives an overview of how to plan studies to avoid bias. More specifically, what we generally use models for, some tools for building our models, and we'll spend most of the time on sources of bias. So why do we use models? Generally, we'll use statistical models for one of three purposes. We want to test a hypothesis, make an estimation, or make a prediction. We may want to build a model to test if an exposure is statistically associated with an outcome, for example. This can extend to multiple hypotheses, and we need to be careful about the interpretation of significance measures when we test many hypotheses. For estimation, we may want to build a model to estimate the effect of an exposure on an outcome. How does being exposed to cigarette smoke affect the risk of getting lung cancer, for example? Closely related to that, we might want to use a model to predict a future outcome. If we know a person's risk of getting lung cancer is affected by how much they smoke, we can estimate the probability that they're going to get cancer at some point in their life. Or perhaps we could develop a blood test that would predict if a person has been infected by HIV. Statistics play an important role in tests like this. Now, as remember, if you fail to plan, you should plan to fail. Develop a model and plan it carefully before you begin to collect data. Convenient samples are often what we're left with when we fail to properly plan a study. Also, scientists are always learning and are often tempted to introduce new hypotheses into a study after the data has been collected. This isn't necessarily a bad thing because we're always continually learning and updating our understanding of the systems we're studying, but it can lead to problems in the analysis, so just be careful when that happens. You can also end up with unexpected biases when using a data set for a secondary analysis, or when combining several data sets into a larger whole. Just exercise caution because the resulting analyses can be plagued by difficulties, including the sample size being too small to answer the questions the study leaders would like to ask. For example, they may be unable to test the hypotheses set forth at the beginning of the study with any reasonable level of statistical power. This often arises out of a lack of focus when they want to test every single hypothesis that you can think of. Also, when collaborators are brought into a study, after it's begun, it's often discovered that important exposures have not been collected. Sometimes the most important exposures are missing altogether or are hopelessly biased. Also, we can, if the study subjects making up the samples suffer from a lack of definition, they don't represent the population we plan to study, perhaps because the primary outcome has been biased or because our sample doesn't include enough variation from the population under study. Poor representation of the population we would like to study is often a function of poor selection of study sites from which to collect the data. Next, many important variables may have large amounts of missing data. This can be a problem, especially on the next point if our missing data in the sample are not missing at random. Well, yeah, that's can be a big problem. Many important variables can often be poorly defined, leading to heterogeneity in what is actually gathered at different study sites. Moving to our next point. For example, two different sample collection centers using two different kits and two different protocols to measure blood sugar levels in study subjects may result in systematic differences in blood sugar readings between the two studies, and between the two sites, rather, in our single study. Similarly, to poorly defined variables, a lack of data validation can lead to varying data quality at different sites. This can result in some sites presenting with an excess of issues described above, or it may lead to data that are so noisy that they are essentially useless. So let's talk a little bit about directed acyclic graphs, or DAGs. So a DAG is a planning tool used to develop your model before you start collecting data. It's a nice way to visualize how you think the biological system works. It can be a useful tool for sharing complicated models with others. It doesn't require any equations or anything like that. It's directed, meaning that there is a direction to the relationship. For example, in here we see that height causes increased weight. Increased height causes increased weight. It's acyclic, meaning that cycles are prohibited. So if your height causes increased weight, your increased weight cannot influence your height. The outcome is typically located in the bottom right corner, and all predictors that cause the outcome under the hypothesized model are up and to the left. This causation starts in the top left corner, and the chain of influenced variables flows down and to the right. Of course, as George Box said, all models are wrong, but some are useful. You aren't going to be able to make a model that correctly captures the biology of what is actually happening, but you should be able to include enough of the major causes of an outcome to make your model useful. This is an aside, but you also want to be careful with the language you use when presenting your model and findings. It's safe to say that genetics and environmental factors cause changes in height, but any statistically significant genetic variance or specific environmental factors that you find to be associated with the outcome, you want to use the word associated. It takes a lot of evidence before you can say that a genetic variant or a specific environmental factor causes an outcome. So just be careful with your language. People are very literal about that. So we talked a little bit about bias already, but your statistics, as well as the data from which those statistics are derived, are biased when the difference between your estimator's expected value and its true value is not zero. Put another way, bias can be thought of as resulting in a systemic difference between a statistic and the true population parameter. So there's a systemic difference between a statistic and the true population parameter. So if the true mean height among males in your population is 5 feet 11 inches, but the way you collect your data results in a consistently higher mean height, then your data and statistics will be biased. To put a finer point on this example, if you only collect samples at basketball camps for aspiring college athletes, you can expect to get a significantly higher average height. A sample you collect like this is not going to be representative of all males living in Frederick, Maryland, or even all males that attend Frederick High School. This is just one type of bias, but hopefully you get the idea of what we're talking about here. So confounding, we use this term a lot. It occurs when there is a difference in the frequency of the outcome in two populations, irrespective of the exposure. So whether or not they are exposed to whatever factor it is you're looking at, there is a difference in the outcome for the two populations. This can induce a false association between the exposure and the outcome. So this pathway here is called a backdoor pathway. Even though the exposure does not cause the outcome, it may still appear as if it does, and this is commonly referred to as Simpson's paradox. A great example of Simpson's paradox, or confounding, is a British study from the 1970s that tracked numerous environmental exposures and their association with all-cause mortality. In the study, they observed an unexpected observation. Women who smoke have a much lower mortality rate than women who don't smoke. So exposure to smoking appeared to cause increased longevity. As they dug deeper into the data, however, they realized that age was confounding the association. When they accounted for age in their statistics, the unexpected observation completely disappeared. So the problem was that age strongly influenced whether a woman smoked or not. So age affected the exposure, whether the women were smoking or not. So therefore, older women were much less likely to be smokers than younger women. There had been a change in societal norms of what was acceptable and what was not. And older women were less likely to be smokers. So, also, older women, age here again, also have a much shorter life expectancy than younger women. So this causes increased mortality. Even taking the adverse effects of smoking into account, this is still, they have a shorter life expectancy than younger women who smoke. So age caused more older women to die, and age caused more younger women to smoke. If the study authors had not collected the age of the women in this study, they could have ended up with unhelpful data. Likewise, when we are designing a study, we want to make sure that any information possible that could confound our results is collected when we gather the data. So let's talk a little bit about misclassification or information bias. This occurs when the disease status influences how the exposure is measured. For example, we could have recall bias, we could have interview bias or data collection bias. So for example, care needs to be taken when writing questions for interviewing subject studies or study subjects. If a question is asked in a way that makes the subject think that you want a particular answer or that one answer is better than another, then they will tend to pick that answer even if it's not true. We also talked earlier about problems that may occur if different study centers collect data using different protocols. These differences can lead to bias that can be difficult or impossible to detect. That would be an example of data collection bias. Proper planning can mitigate this before it becomes a problem. After the data collected, there may be nothing you can do to fix it. An example of recall bias is if you're asking someone how much they smoked 20 years ago, they might remember incorrectly. So let's move on to selection bias. This occurs when the measure of association in the study sample is different than it is in the source population. So for example, individuals must have smoked for 20 years in order to be included in a lung cancer study. The association between smoking and lung cancer may not be evident in this study since everyone in the study is a smoker. Selection bias can be helpful if used properly. There are other questions, for example, that might be interesting to explore in this sample of smokers, like what genetic differences are there between individuals who don't get lung cancer versus those who do? They've got a similar exposure. What makes them different? Again, proper care should be taken when planning studies to be sure you have the right data to answer the questions you really want to ask. Collider stratification bias may occur when conditioning on the collider variable. So this is here in our graph is what we refer to as the collider variable. So this can induce a false association between the exposure E and the outcome O. inducing a false association through a backdoor pathway through some unmeasured factors. So these unmeasured factors, we don't even have to know about them. They just are there, and because we condition on that collider variable, we get problems. So a great example is a study published by Whitcomb et al. In 2009, and they found that increased smoking of mothers is paradoxically associated with decreased infant mortality. So the more the mothers smoke, the better the outcome was in the infants. As they describe in their paper, smoking while pregnant is associated with lower birth weight. Low birth weight can also be caused by a number of other factors that may or may not be measured, and many of these factors may also cause an increase in infant mortality that is much higher than smoking during pregnancy. So these unmeasured factors can cause a much higher increase in mortality. The effect on our statistics is that infants with low birth weight, because their mother smoked, may have a much lower mortality rate than infants with other more serious risk factors. This could make smoking during pregnancy appear to be protective, even if the true effect on mortality is not really. There are lots of different predictor variables that we could consider as potential confounders. And this here is a list of predictors from Frank Harrell that will rarely all be needed for any one study, but you probably want to at least consider most of these when planning new studies. When planning a study, it's helpful to build a DAG that encapsulates your understanding of the system you want to study, and it will help highlight any sources of bias that might creep into and sabotage your analysis. So just be careful when you plan, and you'll be much happier later on when you get to studying your data.